Okay, we have an interesting integral from the Caltech Math Meet 2025, number 12. We have the integral from 2025 to 2024, natural log of the fractional part of x dx. Okay, a couple of unusual things to deal with. First of all, I don't really like having the bigger number as the lower bound. I'm just going to fix that, even though we could just go ahead with it. Just to be polite, let's change that around. So I'm going to bring the lower number to the bottom and bring this up top. To do that, I just need to bring a minus sign out front. Then next, let's deal with this fractional part. Now, if you're not familiar with it, the way it works for the fractional part, if you have something like, let's just say it's 2.34, the fractional part's going to just take the decimal part or the fraction part, and that's going to be 0.34. If it was an integer, something like 3, let's say, that's just going to be 0. There is no fraction part. Another way to look at it is with this formula right here. What's going to happen here, same thing. If we write, so like we'll do 2.34 again, and then if we use a formula on it, it's going to be 2.34 minus the floor of 2.34. But what the floor is going to do is round it down. So for 2.34, it rounds it down to 2. This becomes a 2. Subtract it off, we get the same value, 0.34. So we can use this with our integral, and I think that will help. But one other thing we can use, just notice with the fractional part, if you look at the graph, it's always going to just repeat over and over again because every integer kind of is like starting over at 0, right? We get to 0 here at 3, but when we take the floor of 4, that's going to be 0 as well. And then of course when we get to a value like 3.34 or even 4.34, these values are going to be the same as this, right? It's going to be 0.34, 0.34. So by giving us bounds from 2024 to 2025, they're kind of overcomplicating it for us on purpose. Maybe just throw a little bit of a wrench in it. But we don't need that because the area under the curve is going to be the same between any integer values. So what I can do is let's just change this to have it go from 0 to 1 just because it's going to make our life a little easier. And then what we can do is we'll just go ahead and do the integral using this formula right here. So we'll have an integral going from 0 to 1. And now we'll have this part as just x minus floor function of x. But now this is a pretty good setup because with the floor function, we can just evaluate it. When we have an integral with bounds just separated by 1, we know our x values are all going to be between 0 and 1, which tells us we know how to round this down. In that region, everything is going to round down to 0. So this is just a 0. And so what we can do is just make that go away. And now we're just integrating natural log of x. But this right here, this is one that I can do. That's just a formula. So our formula for the integral of natural log x is just going to be x ln x minus x. And we just need to evaluate from 0 to 1. I think I'll just reverse the sign on it, multiplying the minus sign in. So let's write it as x minus x ln x. And then evaluate that from 0 to 1. So we plug in for the first part, we get 1 minus 1 ln 1 minus plug in 0, we get 0 minus 0 times natural log of 0. Then this is 0. Natural log of 1, 0, so that goes away. Here, natural log of 0 could be a problem. That's going to minus infinity, but we've got the 0 in front. Well, you could do out the limit on this, do L'Hopital's rule, bring in like this into the denominator, and what you get is this is also going to be 0. So putting it all together, this all goes away, and we just have this 1 left over. So for my final solution on this, we just get a 1. Okay, there you go. Good one from Caltech Math Meet. Thanks everyone for watching. Have a good day.